Okay, welcome back. I see that Josef Šivic is arriving. So we are going to resume with the afternoon session on computer vision and trustworthy systems. And the first talk will be given by Cordelia Schmid. She's one of the most prominent researchers in our field. She's a distinguished scientist at Inria in Paris. At the same time, she's with Google Research. What can I say more? She's with the German National Science Academy, and just one thing I can also mention is that I think she's the only person, at least I know, who has received 3 times the test of time paper 1 at CIIRC, and she's going to tell us about large-scale learning from multimodal videos. Thank you.
Thank you, Patrick, for the introduction. So today I'm going to talk about large-scale learning from multimodal videos. So first of all, what are the rationale for using multimodal video representations? If we want to precisely understand the video content, we need to have access to all modalities simultaneously. For example, if we look at the video here, we can see that the man is serving food, but only if we hear the audio, is this Indian, do we know that he's serving Indian food. Another reason for using multimodal videos is that videos come with speech. Speech can be transcribed with ASR, and we can use this data for large-scale cross-modal vision supervision with no manual annotation. So here, this can be, we'll do this later, but this can be used either for pre-training, we have seen some of this yesterday, or what people are looking into more and more is to use this data for zero-shot learning and basically don't have to use any or very few annotated examples for training. Okay, so here in this talk, I'll first show 2 of our recent approaches for large-scale automatic training data collection, then show the importance of the loss function in the models in the context of audiovisual speech recognition, and then terminate with a small example of our work on multimodal transformers for navigation tasks, similar to what we have seen in the previous session. So for the task of vision question answering, if we have, for example, the how to 100 million data set, we only have videos and text, but we don't have question answers. And so here, this first work was doing cross-modal supervision for obtaining videos with corresponding questions and answers. And here, the idea is to use the trick that we have these clips from how to 1 million and the speech transcribed with ASR. And this allows us first to get precise clips with aligned sentences. And then the other information which we use is the, okay, somehow it's also not working, is what we can see here on the right, on the left, is that there's a large corpus of text where people have actually annotated for given paragraphs the corresponding questions and answers. So this has been done for text, and now the idea is actually to use this cross-modal information to leverage these 2 informations jointly and use this to auto-annotate these existing videos. And so what we do here, we have these clips with transcribed ASR. We have now, okay, here, our model, our annotated model, for which we can then train transformers or models that give us back for a paragraph the corresponding answer and the corresponding question. So what we have now, we can take as input a sentence, we obtain the answer and the question. First the answer, so the model looks for the answer in the text, the paragraph, and then the corresponding question. And so we can apply this here to our sentences. We have the sentence transcribed from the video with ASR. We obtain the corresponding answer and the corresponding question. And so what we have now, we have here, we can see here, we have the video clip. The ASR is add some of your favorite sprinkles, give it a mix. And then, given this sentence, we can use the transformer model, which we have pre-trained on this annotated text corpus to generate the question, what can you add to the mix, and generate the answer, sprinkles. And so here we can then auto-annotate this large-scale corpus of 69 million video question-answer pairs. If you look at them in more detail, we obtain an average. The average clip is 12 seconds long and annotated with 1.2 question-answer pairs. And we have a total of this 69 million video question-answer triplets. And if we look at the quality is relatively high. We have 30% where actually the question is correct and matches the visual content. 39 are correct but don't match the visual content, and 31% are incorrect. And so this is enough to pre-train and train a large-scale video question answering architecture based on contrastive learning. So the contrastive learning takes as input positive and negative answers. It can deal with this large-scale corpus. Here are 16 million different answers, and what we have here is input. First, we take as input the video and the question. This is fed as one input to the contrastive learning. The second input is the answer, and then we learn actually what is matching between video question and answers. And this allows us afterwards for video question pair to predict the correct answer. So similar what is done for the clip model. And if you now look at the zero-shot results, so zero-shot means that there is no annotated at all, any annotated pairs. So we just have this completely automatic large-scale corpus which has been scraped from the text, from the web, and the results are reported on state-of-the-art data sets for which we have obviously for the test data only the annotations. And so if we look at what we get if we use random data for pre-training, we can see that basically the results are completely random. And then if we use our data set, we can see, so IVQA is one of the video question answer data sets. We can see top one, 12% of the top one answers are correct. And then if you look at the 10 best replies, we can see 43 of them are correct. So it's not perfect, but it's much better than if we had only no pre-training, right? And then similar for another data set, MSVD, we can also see that the performance is much better than random. And here just an example of the zero-shot results. So remember, here we have no manual annotation of any training data. And so the question is, what is the largest object at the right of the man? Our answer is wheelbarrow. And then what's also interesting is to look at what we would obtain if it was text only. It would be statue. And this is basically because in many images, there are statues next to the person, right? And then the other thing which we can do with this large-scale training data, so what we have seen yesterday, we can obviously also use it for pre-training, right? So there basically the idea is, here the first thing we have shown, that's actually what I'm more interested in, is the zero-shot learning that we can really learn without any annotations, but then we can also use this large-scale data for pre-training, and we can see here in the second row the results for training just on the training data without pre-training. We can see then, if we use this large-scale data set for pre-training, we improve significantly the performance. So this is similar to what we have seen yesterday for language, and here we can also see that this translates nicely to video and language combined. And so basically here we have seen that we can use this weak supervision to exploit the large amount of data available online. You can see that we can use intelligently the correlation between different modalities, to use different types of annotations, to combine them, use them jointly. We've seen that there's excellent performance for results for zero-shot performance. And then one open question, which is very interesting, is to how to further improve this zero-shot performance. So we've seen that it's very good, but basically it's not matching the fully supervised results yet. And then obviously there are a lot of intermediate works where people use only few-shot to clean up the data, but I think in the long term it's really interesting to see how you can match better, even better, the language to the video to clean out incorrect examples. And then another thing, which I'm going to address in the following, is how to extend this to additional domains. So here we've just seen that it was working for the instructional videos, which is how to 1 million, but then there's obviously many more domains, and we're interested not only to cover one domain, but to extend it to more varied domains. And this is a recent work of how to learn audiovisual modalities from image captions. And here, again, the idea is we rely on existing annotations to extend them to video and audio. So here what we do is we transfer image captions to video and audio. And this allows us actually to create, in a weakly supervised way, new data sets of annotated videos, so videos with captions, and also audio sounds with captions. And so what we do here is we start with the seed image captioning data sets. So people have actually annotated this large-scale, relatively clean image captioning data sets. They're not completely clean, like, for example, conceptual captions. So you have these data sets where you have images and corresponding captions. And the idea here is to use these images as initial seeds to search for corresponding videos online. And so the idea is to find frames in videos with high similarity scores, which match the seeds images. And then we can actually crop the corresponding clips from the videos and transfer the image caption to these videos. And so this allows us, for each image, we can not only crop one video, but we can crop many of them, right? So we can really expand the data set, and it can actually go to a very large data set given this procedure, right? And then basically to do the matching between the image and the video, we have some similarity metric and the matching score, but that's actually not very important, the type of similarity matching, and the matching score has to just guarantee that there's some matching with the images. And then, interestingly, what we can see here, basically, if we compare what I said before, the domains in how to 1 million and the domains in our new video CC data set, we can actually see that the domains are much more varied. So if you look at how to 1 million, a lot of things deal with food and hobbies, while in this new data set, there's a much larger distribution of the different classes. And the size here is 10 million, can be further scaled up. It's multimodal, it's truly multimodal. We have both video, audio captions, so it's really, we can really extend it to this truly multimodal data. If you look at other data sets, they're often lacking audio, they're often lacking speech, they're small because they're manually annotated, or there's how to 1 million, then here what we see is that it's much more balanced. And so here, if you look at a few examples, we can see on the left the seed image. So a person throws a pitch during a game against the university. You can see the seed image, and we can see the correspondingly mined videos, which match the captions very well. And then similarly, the next one is the music rap artists perform on stage during the day, during the festival. Again, we can see that the corresponding videos match the caption very well. And so then, as I said before, again, we can use this for zero-shot results. Here it's for video retrieval. So we use a standard method based on contrastive learning to extract video features based on a recent transformer-based architecture, which is VID. That doesn't really matter. And an architecture to extract features from the text. Here it's clip-based, similar to clip-based BERT model. And then we can learn with contrastive learning, based on this data set, the matching between the text and the video features. So we have this large-scale data set, completely automatic. And here what we can see is comparing the different versions. Obviously, if you have no pre-training, then the results don't make any sense. If we have pre-training on how to 1 million, so we do this contrastive pre-training on how to 1 million, we can actually see that the results are significantly lower than if we use our new data set. So they go up from 8.6 to 18.9. That's a really significant increase in performance, and this can be explained by the fact that the data set is much more varied. And then basically what you see here, we call it 1, we recall it 5, recall it 10. You can see, obviously, if you look at the 10 best examples, the performance goes up. And if you look here, basically for recall at 10, we're already at 50%, which is very high. And then the last line, what it shows in the table on the top, if you add, in addition, the audio features, so you can take as input to your training procedure either the video frames, but you can also represent the audio as by using spectrograms similarly to features. So you can also extract features from the audio and then combine them by some type of fusion, either early or late fusion. You can see that this gives you an additional 2% in performance. And similarly, we can also show, I don't have the results here, that you can use the same pipeline to describe audio signals only. All right, so you can also just do retrieval of audio sounds. And then the table on the bottom, you can see actually the comparison of our work to the state of the art, so it outperforms all of the competing state of the art methods. And then something which is actually also interesting, we have extended it to zero-shot video captioning. So this is actually the first time people have performed zero-shot video captioning. So again, we just take this video CC data set, we train a captioning model. The captioning model which we use here is a standard encoder-decoder. So the encoder encodes the video features with a Vivid-based model. The decoder is a classical T5 decoder. And we can see here that again, we get good results for zero-shot video captioning. So we just see this automatically collected data set and use this for zero-shot captioning. We can see that the results with our data set improve significantly over how to 1 million. Here the different scores are scores which are used traditionally to evaluate video captioning. So blue score, CIIRC, Meteor, which measure how similar the predictions are to the ground truth. And so if you look maybe more meaningfully, if you look at the result examples on the bottom, you can see on the top the ground truth. A man is discussing the parts in an engine compartment in a vehicle. Then if we use pre-training on how to 1 million, so I'm going to go ahead and remove this. Okay, not very meaningful. And then we do see the engine bay of an automotive model. So you can actually see what is predicted here is maybe even better than the ground truth, and that kind of also shows the problem, obviously, of evaluating these video captioning models because there's no one specific ground truth. And then second examples, clouds are moving in the sky, and then the one which is pre-trained on how to 1 million is not so meaningful, and the last one, clouds moving in the blue sky, is actually again better than the ground truth. So you can really see that we get these very good results for zero-shot captioning. It also shows some of the problems with video captioning because kind of it's really difficult to evaluate. But it's something which is for real-world applications obviously very important because it really means that you can describe the content of the video and use it afterwards for search. So we have seen with this new data set, we get excellent results for zero-shot audio-visual video retrieval and zero-shot video captioning. We have seen that it's really important which data you use for training and pre-training, in particular if you want to do zero-shot retrieval. And then for future issues is how to further clean the data set and extend it and refine the temporal alignment. There's still work to be done to see how to make the data, the zero-shot data, even better. And then let's move to the second part, is what is important when we train these models. So far I've been only talking about the data. For me, the data is one of the most important things. Basically, as we saw yesterday for language, it's really important what data is used for training. It impacts the performance. There's obviously all the issues which we have seen also yesterday about biases and so forth. But then, of course, it's also important how we set up the loss and the model, right? So basically, that's the second part. And I'd illustrate this with a recent example for audiovisual automatic speech recognition. So again, we've seen this yesterday. Speech recognition is not solved. 4 minutes, okay. Speech recognition is not solved, and so one thing, if we have not clean data, but noisy data, one idea here is to use, in addition, the visual content to inform the speech about what's important there. And so here on the left, we see our model. So here basically takes as input the video features, the frames from the video, the spectrograms from the audio. Here, the model which we have developed is like the bottleneck, the multimodal bottleneck transformer, where the tokens don't interact directly, but via the bottleneck tokens. So we've shown that this works better than early or late fusion. And then a state-of-the-art decoder, which takes this as an input. So this is the model. And what's important, if we train the model, is during training, we have to be very careful how we set up the training so that the model takes into account the visual information. And to do this, we have to mask our tokens and put noise on the audio data, right? If you just use the clean audio data, the task is too simple and it doesn't take into account the visual information. So we really have to make sure that the model pays attention to the visual stream. And so here, if we look at the results, so we have two evaluation settings, one cleaned and one noisy. We can see the top row is with no pre-training, so just learning the model from scratch on this small how-to training set. We're testing it on the how-to test set. The error rate is the word error rate. And what we can see here are two things. The visual information helps in all cases. And then secondly, the pre-training is very important, right? And then thirdly, basically masking out the words further improves the impact of the vision. And so I don't have much time. We can show that our approach outperforms the state of the art. We have collected a small data set where actually the vision is very important to decode the audio. And there we can see that the gain is more significant. And then here maybe just to show what are typical cases where we get an improvement. So this dessert definitely deserves a happy dance. This deserves and dessert. So basically by seeing the dessert, the model, our audiovisual model, interprets the object correctly, right? And so these are all cases when there's like either accents, I don't have the sound here, it didn't play, but either accents or, for example, the motor saw, you have a lot of background noise, and in this case, there's still like, as the person yesterday said, the speech is still not perfect, right? In this case, the speech is still not perfect, and here, then the video can help. Okay, and then, well, we have seen that actually vision improves. It's important how to set up the pre-training and training losses. And what's interesting is to see how we could use the visual cues to further improve the performance. So here we have a gain, but it would be nice to even push the gain further, investigate this even more. And then the last part is actually to show that these models, this is what we have seen in the previous session, can be also used for navigation tasks. So we've seen, now I have one more minute. We've seen, okay, I can have a bit more, like people also talked a bit more. We have seen that basically before the transformer architectures could be used for pre-training language and vision models, but here the idea is that we also want to use it for navigation, right? And so here the idea was to design a fully based transformer model for predicting the actions. And so the idea is we take as input the text, so the instructions go straight behind the couch, the history, so what has been seen previously, the current observation, and then we predict the action, right? And so it's actually a very similar model, which is then used to predict the action. And the trick here is that we have the history of what has been observed before with the corresponding actions, and this allows us to remember what has been seen before. Okay, so here, this is our hierarchical model. I skipped this. It's also, again, important to have different losses for training and pre-training as before. So it's actually the message is hold. Here we can show that our approach outperforms the state of the art. Has been winning the Reverie and Soon challenges at ECCV 2021. And maybe, so what's interesting is the same things, basically, pre-training is important and the losses which are used are important. And then two extensions of what is missing here is generalization to unseen environment, right? If you have this transformer, it memorizes what we have seen so far, but if you go to a new house, it hasn't seen the new house before. So it's really not very well, cannot generalize very well. And so here, what we have been adding is adding how to build a map on the fly and add this map. So construct, while we're navigating around the environment, construct a map, and this helps us actually to see what's new. And I think this is kind of interesting, is to see how to combine these architectures which memorize with something where they learn something new, for example, here, the map. And then the last thing is how to apply it to real robots, and this is just take one last video. So basically this approach, HiFormer, achieves state-of-the-art on RL bench in single and multitask settings, but it also achieves excellent results on a real robot. So here we have a human instruction. So somebody says, press the red button, then press the black button, and press the white button, and the robot actually executes it well without having seen this exact sequence before, right? So this exact color sequence hasn't been seen before. So this is like a first attempt to port this vision language navigation to a real robot, and it kind of works here, so we were very happy. What's actually also interesting, we only fine-tune a very small number of robot demonstrations, so 10 demonstrations per variation. And what's really important and what brings a lot of gain is this pre-training on the error bench. So the error bench is quite different from the real robot environment, but it still brings a significant gain. So again, basically the message holds, pre-training helps, and these architectures are really able also to be used for navigation. Okay, thank you.
Let's take one question in the room. I have one then. So it's impressive to see how much one can get out of multimodality without annotation. But yet there is noise, there is misalignment. Sometimes one modality sees something which doesn't exist in the other one, etc. Can you comment on the sort of the uncertainty or the noise it can also introduce and how to accommodate it?
I think basically what I've shown this evaluation. So if you have roughly 50% of the noise, then the model can handle it, right? It's kind of something we have observed several times. If the noise is not the majority, the model can handle it, right? And so basically, if it's uncorrelated noise, I have the feeling that it can handle it quite well. And I think the main problem of the performance is more the gap between the missing examples and the examples which are there, right? So visual question answering, if you haven't seen this precise domain, it doesn't work, right? So it's not so much the noise, I think, which hampers you, because the noise is uncorrelated, right? And if the noise is uncorrelated, it doesn't make the performance drop too much. But what's really important is that the missing information, right? I think that's for me. Okay.